is yet to come. Okay. Then we started talking about the difference between chemical processes and physical processes, right? So up here, what is rust? That's a chemical. Boiling salt water? Physical. Melting steel? Baking bread? Awesome. Chemical or physical property? Flammability? Chemical, right? Because once I burn it, its composition has changed, right? I burn the wood. Do I have wood anymore? Nope. Sweet. Density? Physical. Conductivity? And melting point? Physical. Questions about those? Cool. All right, so now I want you to talk to the person next to you about these two things. The law of definite proportions and the law of multiple proportions. Okay, and what I'm going to do, you can go ahead and talk. I personally like music, and my go-to is sounds, not that make dogs go crazy. Bring it back. All right, so who wants to give it a stab? What is the law of definite proportions? Yeah.
That a certain compound will always have the same proportions by mass of the elements that make it up.
Awesome. Are you guys here for Chem 105? Sweet. Jump in. I already told them that if some people have to climb over them, it's their fault because they're the ones who sat on the end. So. Yeah, all right. So that was perfectly stated. So the law of definite proportions means exactly what it says. The proportions for a compound, the proportions for the elements in a compound are defined, right? Definite proportions. No matter how much water you have, if you have a glass of water or a lake of water, okay, as long as it's pure water, your proportions of hydrogen to oxygen are going to be the same. Okay? Now we know that because we know water is H2O, but did they know water was H2O back then? No, because they didn't even know what atoms were. All they could do was measure the masses of stuff and realize that the proportions of masses were always the same. Okay? Sweet. Law of multiple proportions. Thought so. Okay, do you want me to explain? Oh, go for it.
Is that the combined small whole number ratio?
Yes. So I'm going to try and explain this as best as I can. Okay, so law of definite proportions is dealing with a single molecule, like a single type of compound, right? The law of multiple proportions is dealing with different compounds made from the same elements. So for example, if I can react nitrogen and oxygen, I can get 3 different gases. Well, I can get more than that, but let's say I can get these 3 different gases. Now again, we know that it's NO and NO2 and NO3. They didn't know that. They just knew that they had 3 gases that were different. Okay? They realized that if they take the mass ratios of oxygen to nitrogen for each of these, let me do that. So what would the mass ratio be, oxygen to nitrogen? This is like 16 over 14, right? I'm just pulling that off the periodic table. 32 over 14 and 48 over 14. What do you notice about these ratios?
They're factors of...
They're multiples of each other. These proportions are multiples, hence multiple proportions. Right? So reacts 2 elements together, we can get multiple compounds, okay? But the ratios of elements, or of masses of elements in those compounds increase, or their ratio of the ratios is small whole numbers. Does that make sense? So what does that teach us if all we knew was mass? What does that show the existence of? Atoms, right? What we realize is that there isn't any NO 1.5. Right? Because these ratios have to increase by small whole numbers. So that says that at any given time, if we want to add oxygen, we have to add a discrete amount of oxygen. What do we call that discrete amount of oxygen? An atom. Does that kind of make sense? Okay, so step back, umbrella time. Okay, definite proportions is 1 compound. The proportions of masses between elements is always the same. Multiple proportions is same elements, multiple compounds. The proportions of masses increase by factors of small whole numbers. Yeah?
Is there an experiment with those that we need to know?
I don't think so. No. I put all the people you're supposed to know on this, so we'll talk about them. That's just based off of the study guide. All right, here we go. Y'all ready? Get smaller. There we go. All right, tire pressure is measured with 4 different gauges. I deleted one, so 3 different times. The actual pressure is 20 psi. Which of these is accurate, precise, both, or neither? Ready, go. Alrighty, bring it back. Sweet. Okay, so what do we got? What's the first one? Whoa. Whoa, who's wrong? Who's right? How do we figure out if something is accurate? You take the average of these numbers and you compare them to the actual value. Okay? That's how you figure out if something is accurate. That's why we can say those are technically accurate because their average is right on target. Does that make sense? I know it sounds stupid because none of them are close to the actual value, but that's our definition of accurate. So when you take the average of these, what do you get? 20. Is that close? Is that within 1% of the actual value? Yeah, so we call that accurate. Does that make sense? Okay, so based on that, what is this guy? Awesome, this one is both. Why? Because all of them are within, so if I take the average of these, the average is close to 20, right? It's like 19.9 something. And so because it's the average is within 1% of the actual value, that's accurate. And then how do I figure out precision? Who wants to tell us? Yeah.
If the values are close together within a 1% standard deviation.
Awesome. So yeah, and so the way that we kind of translate that is take their average, are all of them within 1% of their own average. Does that make sense? So for either of these definitions, what do you have to do? You have to take the average. It's just a matter of what are you comparing the average to? Are you comparing it to the actual value? Then that's accurate. Are you comparing it to the values you measured? Then that's measuring whether or not it's precise. Does that make sense? Awesome. So what's this last one? That one's precise, but it's not accurate, is it?
Far from it.
Far from it. Okay. How do we feel about that? How do y'all who are sitting on the stairs on the side feel about that? Less comfortable about that? Okay. All right, let's keep going. Identify the significant figures, and then, so do all of these. Okay? Ready to go. Testing. How many of you had disagreements with the person you're sitting next to? Okay. Also, somebody from Arizona just texted me and said, hey, Jeremy, play Whatever It Takes again. I don't know who it was, though, because I don't have your number saved. So, sorry. All right. So let's talk about this. So when Dr. Seavey taught about significant figures, he put like 17 million rules on the board about zeros. Okay, so I like to stand by 2 rules because it answers all the questions. Okay, so I don't know if this is still a point of confusion for people, but if it is, let's go for it. So you have leading zeros and you have trailing zeros, right? Then you have this thing that's in the middle, but everybody knows that's a significant figure, right? So you have leading zeros and trailing zeros. When do leading zeros matter? Leading zeros never matter. Leading zeros never matter, ever, 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 ever. Okay? And when I say leading, I don't mean leading the decimal, I mean leading the number. The first non-zero number. So like, these don't matter, ever. Okay? What about trailing zeros? When do trailing zeros matter? When there's a decimal. Okay, with those 2 rules, you can answer all the questions. Sound good? All right, let's do it. So how many significant figures here? 3. Awesome. Here? 4. Okay, because there's a decimal, therefore, the trailing zero matters. Okay, trailing zeros matter if there's a decimal.